For section 7.1 in our calculus BC study, we are going to start out by learning how to solve differential equations. Now, much of our experience in pre-calc has been with finding different models to model different types of data. We started with the most simple type, which is linear data. If we had linear data, we could write a linear model, and we can in turn use that to make predictions for some whatever particular topic it may be from. Could be an application from science or business or whatever the case may be. And then as we work through our pre-calculus work, we enhance that to use other models like exponential models, quadratic models, trigonometric models. And bottom line is once we take our data and use it to find a model, we can use that model to make predictions about phenomena, like I said, in science or business or whatever category it might be from. So what it boils down to, though, is sometimes in life the information that we collect data-wise is in the form of a rate. Instead of a form of data points, we're in a form of a rate. And sometimes it leads us to what we call a differential equation, which is ultimately just an equation that involves a derivative. Okay. So for instance, if I were given a differential equation like, say, dy dx equals, say, secant x tangent x minus e to the x, the question is, if this is our differential equation, if this describes the rate at rate at which y is changing with respect to x, is there a way that I can get from the derivative, if you will, back to the original equation? Because if I can get back to the original equation, then I can use it to make predictions, etc. So the answer in some cases is yes, and in some cases not so much. We have to do some other work. But bottom line is the ideal case scenario, if we're given a differential equation, is that if we can write an equation for y that this is the derivative of, then we're in good shape because we can use that equation, like I said, to make predictions. So the general procedure when solving a differential equation is going to be the following. We're going to call this what we call separation of variables. So that's going to be our general technique. So we're going to write separation of variables. And what it boils down to is we're going to take the dy dx and we're going to split it into its two differentials. So we're going to take the dx and we're going to multiply both sides by dx. And so our sentence will read dy, and then over here secant x tangent x minus e to the x dx. Now in this particular case, there's nothing with y over here on this side, and sometimes there is, which we'll see in a few minutes. But the bottom line is, as long as all this stuff is in x, and we have dx here, then we're in good shape. Now, step 2 in the separation of variables, after separating the differentials and getting the x parts with x, if you will, and the y parts with y, which in this case didn't need to happen, then we are going to integrate both sides, because ultimately, keep in mind, if we have the derivative and we want the function it came from, it's going to be an antiderivative situation, so it's going to be terribly surprising that we're going to integrate at this point. So doing that, we're going to have, keeping in mind the argument here is really just 1, so the antiderivative of 1 with respect to y is y, and then over here, the antiderivative of secant tangent, we know it's secant x, and the antiderivative of e to the x is itself. And we get that, and of course, it's an antiderivative. It's an indefinite integral here, so we're going to have a plus c on here. So ultimately, we get y equals secant x minus e to the x plus c. And that's it. So I mean, we've set out to what we wanted to do. We have an equation y whose derivative is secant x tangent x minus e to the x. And ultimately, when we do this, of course, we get a family of functions that could be possible answers to this. Now, in a few minutes, we'll also look at what we call an initial value problem, which means that we're going to be given some value for when x is something, that y is something, which in turn will allow us to find this value c for a specific instance. But in the case of just solving a differential equation in general, your whole goal is to just find an equation for y. Okay. Let's look at another. How about if we do dy dx, or this is dy dt this time, cosine t e to the sine t. So in this particular case, we can see that if we separate our variables, we're going to have cosine t e to the sine t dt. And this time, if we integrate, we're going to get y again over here. And then over here, we have to do a little bit of work, because you notice that this is not a known derivative. So since our sine is here and our e argument, good u substitution here would be sine t, because we know that du would be cosine t dt, which is exactly what we have to get rid of here. So in terms of our u equation here, we'd have e to the u du, straight up change, u replaces the sine t, cosine t dt is replaced by du, and with that we can anti-differentiate and we can get, of course, e to the u plus c, and so our answer over here on the side is e to the sine t plus c. And we're done. So in this case, the answer is relatively simple because we have just y on the side, which is ultimately what we want. We want to get y by itself, which we've done. We've anti-differentiated both sides, and we've gotten our result. Now, one thing that's kind of nice is that when we have a differential equation, we can certainly check this, because if we have this situation, if we were given this in the first place and we wanted to get the derivative, we would just go derivative with respect to t here would be dy dt, e to the sine t we know is itself, times the derivative of the argument, and we know, of course, c's derivative is 0, and so notice what we ended up with, exactly the same thing we started back, so this part would be what we call the check. Alright, so what we're going to look at next here then is we'll extend this to what I mentioned earlier, which is an initial value problem. So let's take a look at this next one we'll do here is call it dA dx, and it's 10x to the 9th plus 5x to the 4th minus 2x plus 4. And they tell us that a is 6 when x is equal to 1. So we're given an initial value, which makes this an initial value problem, which ultimately is no different than in solving a differential equation, except for in the end we're going to find c. So we'll still follow the same procedure, which is separation of variables. And if we anti-differentiate both sides, we're going to get a over here, and over here we're going to get x to the 10th plus x to the 5th minus x squared plus 4x plus c. And now in an initial value problem of any sort, as soon as we anti-differentiate both sides, we need to plug in the initial condition immediately, and do not wait. So ultimately we're going to get 6 here. If we put a 1 in for all these, we're going to get 1 plus 1 minus 1 plus 4 plus c. And ultimately those two cancel out, of course. We'd have 5. 5 plus c equals 6. And so if we subtract the 5, we get c equals 1. And hence my final answer then is a equals, and again the final answer is the equation, it's not c. C is part of the final answer, but ultimately we're going to get that as our final equation. So that would be the solution to the initial value problem. And again, keep in mind that what we found here, or what we set out to find is, given this differential equation, can we find the function it came from that satisfies this initial condition? And we can check to see if that's the case by putting in 1 here. So we got 1 plus 1 minus 1, and so far that's 1, plus 4, that's 5, plus 1, that's 6. So it does satisfy the initial condition. And if we differentiate this, we had better get this. And we can see that this would be 10x to the 9th plus 5x to the 4th minus 2x plus 4. So indeed we found an equation that has this as its derivative and has this as its initial condition. And it satisfies this point, if you will. So with that said, we'll look at one more here. We'll look at the equation du dx equals the square root of 2 plus cosine x. And we're given an initial condition of u equals -3 when x equals 0. Okay. So now, one of the issues that we have with differential equations is all three problems that we've done so far have relied on the fact that we can actually find an antiderivative for the integrand on the right side. So if we start this problem, if we look at 2 plus cosine x dx, the issue here is when we try to anti-differentiate this is not a known derivative. If we try to substitute here the 2 cosine x, we're going to end up with a sine in our du, which there is no sine to deal with. So bottom line is there's really no good way to find an antiderivative for this at this point. So the question is, what do we do? Well, any integral, any antiderivative, if you will, can be written in terms of the integral. And ultimately the technique is going to be as follows. We're going to just keep this as our answer here, but to evaluate it, keeping in mind that when we do evaluate this, we'd get some value of c here. And so if we want an antiderivative that satisfies this initial condition, then what we're going to do is we're going to write the integral, and we're going to write it in terms of a dummy variable. So we're going to write cosine t, if you will, and we can use t or whatever letter we so choose. dt, we'll change the x's to t's here. And then we'll use x as our upper limit. And what we're going to do with our lower limit is we're going to let the lower limit be whatever our initial x value is, which is 0 in this case, and then ultimately on the u value, or whatever independent or whatever dependent variable it is, whether it's u or y or whatever the case may be, we're going to just take that, we're going to take this integral, and we're going to subtract that y condition or that u condition in this case. Okay? So here's why that works. First of all, if this is our integrand, keeping in mind writing it as an integral here gives us the antiderivative. I mean, this is the antiderivative of this, even though we don't have an explicit formula for it. Okay, this expression right here represents the antiderivative of radical 2 plus cosine t. Okay? Now here's why the initial condition works, because if we have 0 here as our lower limit, and we take our 0 as our initial condition and we plug it in, then this is going to be the area from 0 to 0 of this curve, which is ultimately 0. And of course, what's 0 minus 3? It's negative 3. So it does satisfy the initial condition, okay? And also it represents the antiderivative of the original equation, which was our differential equation, du dx equals radical 2 plus x. Okay? Let's look at one more of those, that type where we cannot find the antiderivative. If we're given something like g prime of s is equal to the cube root of tangent s, and ultimately keeping in mind g prime of s is just this, is just basically dg ds, and I would probably write it like that as such before we get started here, because we still want to follow our same method, which is separation of variables. And so if we do that, we can separate our variables and be at that stage. And from here, we can integrate. Now, keeping in mind that integrating is nice, but we can't integrate this because this is not a known derivative. Substitution won't work. It's not going to work with any of our methods that we know at this point. So what do? Well, we just write it as an integral. So we're going to write it as tangent, cube root of tangent, that is tangent t dt, and we'll have s as our upper limit. And then the initial condition that we're given in this problem is going to be g of 0 equals 4. Okay? In other words, when s is 0, g is 4. So that means that s value here is 0, and if I add a 4 on the end, then my initial condition will be satisfied, because again, if I have a 0 here and I plug in a 0 to here, I'm going to have 0 to 0 of this curve, which ultimately is 0, and I'm going to have 0 plus 4, which gives me 4, which again satisfies the initial condition. And it also gives me an expression that represents the antiderivative of our original function. So even though we can't come up with an explicit formula like we did in the first few problems, okay, we still have an expression that we can use, because this is ultimately a g function in terms of s. So if we wanted to know g of 5, say for instance, couldn't I find the answer to that? Can't find it by hand because I can't use the fundamental theorem because I don't have an antiderivative for this, but ultimately this could show up on a calculator problem, because this is a problem that your calculator can do. It's a definite integral. So if we wanted a value for g at some particular instance of s, then we could certainly find it, because we have a calculator that will perform that action. Okay, so that is the gist of our work for today, dealing with solving differential equations and initial value problems. So good luck.